Meet Claudius Ptolemy, the ancient world's ultimate compiler. A Greco-Roman mathematician, astronomer, and geographer active from 100 to 170 AD, Ptolemy transformed over 8 centuries of scattered Babylonian and Greek observations into unified, predictive mathematical models. Rather than relying solely on observation, he constructed elegant geometric frameworks mapping both the Earth and the cosmos. His masterwork redefined scientific thought, establishing a definitive canon for the heavens that governed astronomy and geography for more than 1,400 years. In 2nd century Alexandria, the Roman Empire's ultimate intellectual hub, knowledge converged from across the known world. Amidst trade routes, the Great Library, and the Temple of Serapis worked Claudius Ptolemaeus, a scholar blending Roman citizenship with Greek-Egyptian roots. Utilizing Alexandria's vast influx of data, Ptolemy conducted rigorous astronomical observations at Canopus between 127 and 141 AD. By recording his precise planetary parameters onto commemorative pillars, he turned the Alexandrian crucible into the cornerstone of ancient science. To map the cosmos, Ptolemy established the 5 core postulates of his Almagest. At the heart of this geocentric blueprint lies a perfectly spherical, completely stationary Earth, anchored at the exact center of the universe as a mere mathematical point against the vast expanse. Surrounding it, the celestial heavens rotate as a single, unified sphere. Reasoning that any terrestrial motion would generate destructive winds and displace falling objects, Ptolemy defined a motionless world around which the entire universe eternally revolves. To reconcile complex celestial observations with ideal circular motion, Ptolemy devised 3 geometric mechanisms: the epicycle, the eccentric, and the equant. While epicycles explained retrograde loops, offsetting Earth via the eccentric accounted for variable planetary speeds and unequal seasons. The equant further decoupled uniform speed from the physical center. By shifting the center of uniform motion, Ptolemy achieved predictive accuracy within 10 degrees. Deliberately sacrificing physical realism to save the mathematical appearances. Moving beyond pure mathematics in his planetary hypotheses, Ptolemy transformed the cosmos into a solid, physical reality. He proposed a universe containing no empty space, built from contiguous, nested spheres made of ether, an incorruptible, transparent fifth element that carried planets like gems set in thick glass. Using this nested physical framework, Ptolemy calculated the absolute dimensions of the ancient universe, determining that Saturn, the outermost planet, orbited at a distance precisely 19,865 times Earth's radius. Recognizing that hand-drawn maps inevitably degrade through generations of copying, Ptolemy pioneered history's first geographic information system by prioritizing data over drawings. In his geography, he compiled the exact numerical coordinates for over 8,000 cities, rivers, and mountains across the known world. To anchor this vast network, he established a global grid, deriving latitude astronomically from the longest day of the year and measuring longitude from a western prime meridian. By transforming physical geography into mathematical code, Ptolemy created a timeless, fully reproducible map of the world. Ptolemy charted the oikoumene, the known inhabited world, within precise geographical boundaries. Anchored to the west by the Fortunate Isles at the prime meridian, his grid extended north to frigid Thule at 63 degrees north, south to Ajasimba in Central Africa at 16 degrees south, and far east to China bordering the Sinus Magnus. Crucially, Ptolemy envisioned the Indian Ocean as a massive, landlocked body of water, enclosed to the south by an unknown continent connecting Africa directly to Asia, framing the ultimate terrestrial limits of ancient geography. To project a curved Earth onto a flat surface, Ptolemy established the mathematical rules of cartography. He presented 2 key solutions: the conic projection, a practical model using straight meridians and curved parallels for a single hemisphere, and the spherical cloak, chlamys, a complex framework employing curved meridians to capture a globe's 3-dimensional distortion on a flat page. By defining the trade-offs of scaling and proportion, Ptolemy provided mapmakers with a blueprint for translating physical reality into 2-dimensional media. By rejecting Eratosthenes' accurate Earth circumference for Posidonius' smaller estimate, Ptolemy committed a fateful error. Stretching the Mediterranean to 62 degrees of longitude instead of its actual 42, he expanded Eurasia across 180 degrees, radically shrinking the vast ocean to its west. Centuries later in the 15th century, this understated distance provided Christopher Columbus with the mathematical confidence to sail west to reach Asia. A historic leap driven by ancient geography's most consequential miscalculation. In his exploration of light, Ptolemy bridged ancient intuition with pioneering experimental science. Adopting the extramission theory, he believed vision occurred via rays actively emitted from the eye, perceiving objects through direct geometric contact. Yet despite this physiological misconception, his optics featured groundbreaking quantitative research. Ptolemy meticulously measured and tabulated the precise angles at which light refracts when passing between mediums of differing densities, such as air, water, and glass. By applying geometry to the behavior of light, he established one of antiquity's earliest experimental frameworks for physical science. In his Harmonica, Ptolemy bridged music theory's great divide between Pythagorean mathematical purity and Aristoxenean ear-based perception. Seeking a middle ground, he argued that mathematical reason and empirical observation must validate each other. Using the monochord to conduct physical experiments, Ptolemy developed the intense diatonic scale, a system of precise tuning ratios that established the groundwork for modern just intonation and harmonized abstract geometry with human sensory experience. While forgotten in the West during the early Middle Ages, Ptolemy's masterwork, the Mathematique Syntaxis, found new life in 9th century Baghdad under caliphs like Al-Ma'mun. Renamed Almagest, the greatest, his texts were translated into Arabic, but Islamic scholars did far more than preserve them. Thinkers like Ibn al-Haytham actively challenged his models, penning doubts concerning Ptolemy to critique physical inconsistencies like solid spheres and non-uniform equant motion. By putting classical theory to the test, Arab scholars ensured astronomy continued to evolve. At the Maraga Observatory, Islamic astronomers like al-Tusi and Ibn al-Shatter rejected Ptolemy's equant for violating uniform circular motion. To resolve this flaw, al-Tusi invented the Tusi couple, a brilliant geometric mechanism generating straight-line oscillation purely from nested, uniform circular motions. By eliminating the awkward equant while preserving physical symmetry, the Maraga revolution redefined celestial geometry. Centuries later, Nicholas Copernicus utilized these structurally identical mathematical models to construct his heliocentric universe. In the 1970s, physicist Robert R. Newton sparked fierce debate by branding Ptolemy the most successful fraud in the history of science, claiming his observations were back-calculated to fit his models. Yet modern historians reject this charge as anachronistic. Ancient compilers were not writing modern lab reports. Their goal was to synthesize, idealize, and select representative data to reveal universal geometric truths. Ptolemy was crafting an enduring teaching paradigm, bridging messy real-world observations with ideal mathematical design. Though modern science eventually superseded his physical universe, Ptolemy's mathematical framework dominated human thought for over 1,400 years, longer than any other scientific paradigm in history. By stripping maps of drawings and reducing geography to numerical coordinates, he established the conceptual foundation for modern geographic information systems. Ultimately, Ptolemy's enduring legacy lies in his method, training generations in scientific rigor through the relentless drive to harmonize messy empirical data with elegant mathematical models.